Yeah, I'm sharing my screen. Yeah, today we'll discuss about the how to write the test bench for sequential circuits. Okay, test bench for sequential circuits. Okay, so if you see the test bench for sequential circuits, one second. Test bench for sequential circuits. So first how to write means here first I'm writing for I'm taking one example of D flip flop and I'm writing the test bench for this. Okay, so how to write means first module that is TB. Okay, module TB D underscore TB. So what is my test bench? So you can write the module name that is D flip flop. Okay, D underscore flip flop or D underscore flip flop underscore TB or D underscore TB. Okay, whatever may be that. So D underscore flip flop underscore TB. Okay, this is my module name. Okay, and step 1. So what is step 1 means? You need to declare the internal variables. Okay, so you need to declare the internal variables. Declare the internal variables. Internal variables. Okay, so you already seen that port rule connections. No? So port rule connections. If you see the port rule connections, so in the top module, the input should be netted data type. No, so input should be netted data type. Okay, and output should be wide data type. Okay, so so I'm writing this initializing the inputs. Suppose if you consider any D flip flop, so if you see the D flip flop, what are the inputs? So that means inputs are D, okay, and output is Q, and my clock is there. One more clock is there. So this is my design. Okay, this is my design. Test bench is nothing but what? So for test bench, I am writing for this D flip flop on the top module. Okay, so on the top module, and you have what test bench inputs are also there. So test bench inputs, these are the test bench inputs. So and let us take D underscore in and clock. Okay, clock, and one more reset is also there. Okay, reset is also there. Okay, and next the q and q bar are nothing but my outputs. Okay, so you need to declare the input. So we already seen the port rule connection for the top module. So this should be netted data type, no, and this should be, sorry, this should be reg data type. Okay, so for the test bench inputs, this should be reg data type, and whatever the output is there, this is netted data type. Okay, so here first you need to declare the internal variables. Okay, so input you need to declare with netted reg data type. Okay, reg. So what are my input for the test bench? Clock, reset, okay, and D in. These are my uh, inputs. Okay, and what are the outputs? Wire q and q bar, q underscore bar. Okay, so this is my first step is nothing but you need to you need to initialize the internal variables. Okay, you need to initialize the internal variables. Okay, so before that you need to write the sequential circuit. So first yeah, before writing this so I need to write the code for this one. Okay, here I am writing the code for the D flip flop. Okay, so for the D flip flop, if you see the D flip flop, so I'm writing the code for D flip flop. So yeah, I will take some space, and here I will write. Okay, so D flip flop. Okay, so this is my D flip flop. So that is so let us take, this is my D flip flop. So what are the inputs? D is my input, and Q and Q bar. Q bar is my output, and clock is there. This is my clock. Okay, so this is my clock, and how to write? So this is my D flip flop. So how to write like the Verilog code? So that is module. My module name D underscore flip flop. I need to initialize. Okay, so that is input clock. Okay, input clock, suppose reset is there. Suppose if I am using asynchronous active low reset, means this is asynchronous active low reset. So let us take, this is my reset. Okay, asynchronous active low reset. So inputs are clock, reset, and D in and Q, and output. What is output? Output is Q and Q bar. Q and Q bar. Okay. So here, so I am writing behavioral modeling, that is always at the rate passage of clock or negage of reset. Passage of clock or negage of reset. Passage of clock or negage of reset. So here, begin if reset, if not of reset. Okay, if not of reset or reset equal to 0. Okay, so Q initialized to what? Q initialized to 0. I am using non-blocking operator for the sequential circuits. Okay, so you need to use non-blocking operator for the sequential circuits. Else so here, begin. Okay, begin. Okay, so begin, Q is non-blocking with what? D, and Q bar is non-blocking with what? Q bar. Q bar. Okay, this is Q bar is Q underscore bar is non-blocking with not of Q, and end. Okay, end, and this also you need to end. Okay, end and end module. Okay, so I wrote the design. Okay, I wrote the design. Okay, so after writing the design, what you need to do? You need to write the test bench. Okay, so test bench, so input for the test bench you need to declare with reg data type, and output for the test bench you need to declare with the wire data type. Okay, and next, step 2. What is my step 2? Step 2 is nothing but you need to instantiate the design in the test bench. Needs to instantiate the design. Okay, the design in the test bench. So how you instantiate? So that means my design name. What is my design name? D underscore flip flop. No, so this is my design name. Okay, so D underscore flip flop, and instance name. What is my instance name? DUT. And next, so how you initialized in the design? So that means I am using connection by position with order list. Okay, so how you initialize the inputs and outputs, that same order you need to follow in the instantiation. Okay, so how we initialize that is clock, and next reset, and D underscore in. Okay, and next Q Q bar. Okay, Q and Q bar. Okay, let us take, this is Q bar only, Q underscore, not as Q underscore bar, just Q bar. Okay, so this is my variable Q bar. Okay, so I instantiated. Okay, this is nothing but instantiation, connection by position with order list. Okay, so this is the connection by position with order list. Okay, and next is step 3. So what is step 3? Step 3 is nothing but you need to initialize the internal variables. Internal variables. Okay, what are the internal variables? Reg values, that is you need to use initial, begin, and I am using concatenation operator. So in the concatenation operator, whatever the reg variables are there, what are those reg variables? Clock, reset, and D underscore in, that is equal to what? 0. Okay, end. Okay, so initial, begin, and end. Okay, so this is step 3. Okay, step 3. And next, step 4. Okay, just this one second. I think yeah. Here I will continue. Next, step 4. Okay, step 4. What is step 4 means? You need to generate the clock. Okay, so you need to generate the clock. So how to generate the clock? So that means always hash 5, hash 5, this is my delay. Okay, hash 5 is nothing but my delay. Clock equal to what? Clock equal to not of clock. Clock equal to not of clock. So that means I'm generating the clock. Okay, here I'm generating the clock. So one clock cycle, this is nothing but one half clock cycle equal to 5 time units, and next clock cycle is how much? 5 time units. Okay, so that means this is actually 0. After not of clock, this is 5 time units. Okay, so total what is the time period? So time period is from here to here. Time period is I am generating the clock with time period is 10 time units. Okay, it may be 10 nanoseconds like that. Okay, so how much of time scale you are giving, that many nanoseconds you are giving. Okay, so that much if you are giving nanoseconds means the time scale is nanoseconds. Okay, so you are generating the clock. Okay, time period. So what is my time period? Time period equal to 10 nanoseconds. Okay, 10 nanoseconds. Okay, so this is generating the clock. Okay, and next so here next step 5, here I am writing step 5. Step 5, you need to drive your stimulus. You need to drive your stimulus. Okay, so how to drive your stimulus? So that means initial. Okay, initial, begin. Okay, in order to avoid the setup time and hold time, there is a setup time violations and hold time violations are there. Setup time is there. Setup time is nothing but when that means when here the like clock is there. So clock is there, so that means input should be stable before this clock edge. Okay, input should be stable before this clock edge, that is nothing but setup time. Okay, so input should not change. Okay, input should come before this clock edge, then it is nothing but setup time. So when input is changing during this edge, there you will get a setup time violations. Okay, setup time violations. And what is hold time means, after clock edge input should be stable. Okay, that is nothing but hold time. So to overcome this setup time and hold time violations, you are driving your stimulus in the neck edge of clock. Okay, you are driving your stimulus in neck edge of clock. So begin begin. Okay, begin is already there. So begin at the rate neck edge of clock. Okay, neck edge of clock, neck edge of clock. So first what you are doing, this is a active low reset. No, first you are giving reset. Okay, first you are giving reset. So when you are giving reset, so all the outputs will be resetted to 0. Okay, this is nothing but so this reset, which reset I used, asynchronous. This reset is nothing but asynchronous active low reset. Active low reset. So when it will be reset, when reset equal to 0, you are getting Q equal to what? Q is initialized to 0. Okay, when reset equal to 1 only, it will be in the functional mode. That means Q is initialized to D. Okay, so that means first you need to apply the reset. Okay, why? Because you need to make all the outputs to 0. Okay, so at the neck edge of clock, reset equal to 0, and after that at neck edge of clock, so at neck edge of clock, at neck edge of clock, so I am releasing the reset. Okay, reset equal to what? 1. Okay, releasing the reset. Okay, after releasing the reset, first what I am doing, first at neck edge of clock, I am giving the stimulus. Okay, so that means I am giving the input d underscore in equal to what? First 1 I am giving. Okay, so or you can write like this also, 1 tick binary 1. Okay, so 1 bit I am giving. D input is initialized to what? 1 tick binary 1 you are giving. Okay, and next at the neck edge of clock, at neck edge of clock, D in. Okay, so D underscore in equal to what? 1 tick binary 0. Here I am giving the stimulus. Okay, if I am giving the stimulus and end module. So that means that test bench, so this is my design, this is my test bench. Okay, so that means here you see the test bench for sequential circuits. If you see like how many steps are there? 5 steps are there. So last class we seen about the the test bench for combinational circuits. So only one thing is added. What is that? In combinational circuit, clock is not there, but in sequential circuits, we are generating the clock. This only we are adding. Okay, remaining all are same only. So this is you need to follow. First, what you need to do? You need to initialize declare the internal variables. What are the internal variables? So inputs you need to initialize with rich data type, and outputs you need to initialize with y data type, and you need to instantiate your design. First you need to write the program in the design, and you need to instantiate by two methods. One is connection by name and connection by position with order list. Here I am using connection by position with order list. Okay, so how I am doing d underscore flip flop, my instance name, this is design name. What is my design name? D underscore flip flop. And what is my instance name? DUT. So how you declared your inputs and outputs in the design, that same way you need to declare the inputs and outputs. Clock reset D underscore in Q bar. Okay, this is nothing but connection by position with order list. Okay, and next you need to initialize the internal variables. What are the reg variables? Clock, reset, and D in. Okay, so here initialize the internal variables. Initial, begin, clock, reset, D underscore in. I'm using concatenation operator, and I'm initializing to D0 and end. And next you need to, step 4 is nothing but you need to generate the clock. Okay, always #5 clock equal to what? Not of clock. Okay, and next you need to give the inputs. Okay, test vectors, that is driving the stimulus. Okay, you are giving the test vectors to the design, and design will process and it will give the output. Okay, output to the test bench, like that. Okay, so see here, initial, begin at the rate negate of clock. First I am applying the reset. Okay, this is nothing but applying the reset. Okay, and next what? You are removing the reset. Okay, first I am making reset equal to 0, and next I am making reset equal to 1. After that, at negate of clock I am giving one input, and at negate of clock I am giving one more input. Okay, so like this you need to write the test bench for D flip flop. Okay, hope you understood how you write the test bench for D flip flop. And SR flip flop, how you will write? So suppose so design you do. Suppose SR flip flop means you have, so test bench for SR flip flop. If you see the test bench for SR flip flop, so like so how you write the design, that means here SR flip flop. So for the design, if you take, so first I am writing the design. Okay, so if you see the SR flip flop, so this is my SR flip flop. Okay, so S and R. Okay, and next Q bar, Q and Q bar, and this is my clock, passage of clock. Okay, so this is passage of clock, and one more, this is let us take asynchronous active low reset is there. Okay, so first I will write the design. So module. So what is my module name? So my module name is SR flip flop. Okay, so I need to initialize the inputs and outputs. Okay, input first clock, S, R, and reset. Okay, these are my inputs. Okay, output. What is my output? Output is nothing but output. If we are using behavioral modeling, you need to initialize with reg only. Okay, you need to initialize the output with reg. Here I initialize reg, no. One second. Here also we are using behavioral modeling, no. So this you need to initialize reg. Okay, reg data types. Okay, so if you see the port rule connections, so that means if it is behavioral modeling, so you need to initialize the output with reg. Okay, otherwise you will get a compilation error. Okay, Q and Q bar. Okay, so I initialize the input and output. So I am using, that means I am using procedural block always at the rate. So passage of clock or negate of reset. Okay, so negate of reset, begin. So you can use the procedural statements. Okay, here I am using if else statement. Okay, if not of reset. Okay, if not of reset. So here what I am doing, so that means begin q is initialized to 1 tick binary 0, and q bar is initialized to 1 tick binary 1. Okay, so this is complement, no? So complement. So whenever you are writing multiple statements, you need to write with so you need to write with this one. Okay, so this begin and end, you need to write between the begin and end. Okay, else if, okay, else if okay, if s comma r, else if s comma r, begin else if okay, s equal to, so you know the truth table for SR flip flop. Okay, so that means SR flip flop, what is this is qn plus 1, no? So qn plus 1, so that means here so here 0 0 0 1 1 0 1 1. Okay, when it is 0 0, this is memory state, reset state, set state, and unknown means invalid state. Okay, so this is memory state, and this is reset state, and this is set state, and this is indeterminate or invalid state. Okay, this is invalid state. Based on the truth table only I am writing. So this is s equal to 0 and r equal to 0. Okay, r equal to 0. So q is nothing but q. Q is nothing but q. Okay, q bar is same as q bar. You need to use non-blocking operator, non-blocking assignment. Okay, non-blocking assignment. And next, else if okay, s equal to 0 and r equal to, okay, r equal to 1. R equal to 1. Okay, so q is initialized to what? Reset state, no? So the q is initialized to reset state, and q bar is initialized to 1 state. Okay, 1 state. Next else if okay, s equal to what? S equal to 1 and r equal to what? R equal to 0. R equal to 0. So q is initialized to set state, and q bar is initialized to reset state. Okay, reset state. Okay, else if okay, else, okay, else means here, else means what? That is s equal to 1 and r equal to 1 only. So q is initialized to what? 1 tick binary x, unknown condition. Okay, similarly q bar is initialized to 1 tick binary x only, 1 tick binary x only. Okay, and end module. Okay, this is my design. Okay, how to write the test bench? So for the test bench, SR flip flop test bench. Okay, so I think you can write so SR flip flop test bench. First you need to initialize the so SR flip flop test bench. SR flip flop test bench. Okay, so if you see the SR flip flop test bench, so you can write same, so you can follow that same as a D flip flop only. Okay, so module so SR flip flop underscore TB. Okay, so whatever the, so first step 1, what is step 1? Step 1, you declare the internal variables. Okay, so what are the internal variables? So internal variables are so here you have reg clock, next reset s and r. Okay, these are the input, and output you need to declare with y data type q and q bar. Okay, q bar. Okay, and step 2, you need to instantiate. Okay, step 2, so instantiate the design, okay, the design in the test bench. Okay, how to instantiate? So what is my design name? My design name is SR flip flop. Okay, so design name is SR flip flop. So SR flip flop, and my instance name is design under test. Okay, so here how you are declaring the inputs and outputs, the same order I am declaring the inputs and outputs, S, R, Q and Q bar. Okay, so this is nothing but instantiation by position with the order list. Okay, and step 3, you need to initialize the internal variables. Initialize the internal variables. What are the internal variables? Here initial, begin. Okay, so I am using concatenation operator, clock, reset, S and R. Okay, so I am initialized to 0. Okay, end. Okay, and next generate the clock. So you need to generate the clock. Step 4. Okay, generate the clock. You need to generate the clock. So how we are generating the clock? Always #5. Clock equal to what? Not of clock. Clock equal to not of clock. Okay, and you drive the stimulus. So step 5, you need to drive the stimulus. Okay, drive the stimulus. How you are driving the stimulus? So that is initial, begin. Okay, at the rate negate of clock. First you are writing reset equal to what? 0. Okay, you are applying the reset. After that you are releasing the reset. Okay, at the rate negate of clock. Okay, so reset I am making as 1. Okay, after that I am giving the test cases. Okay, so at the rate negate of clock. Okay, I am giving what? So that is S equal to 1 tick binary 0, comma, so S equal to R equal to 1 tick binary 0. Okay, I am giving the test cases. Okay, similarly at the rate negate of clock I am seeing some test cases. Okay, what is my output? I am saying, okay, negate of clock. So here I am giving S equal to 1 tick binary 0 and S equal to 1 tick binary 1. Okay, similarly at the rate negate of clock, S equal to 1 tick binary 1 and S equal to 1 tick binary 0. Okay, similarly negate of clock, S equal to 1 tick binary 1 and R. Here R. Okay, R equal to 1 tick binary 1. Okay, end module. Okay, like this I need to write the test bench. Okay, hope you understood. Just I will show you some test benches. 1 second. See here. I think I shared this Verilog codes, no? 1 second. Yeah, Verilog codes. Okay, so here different levels are there. This is anyway combinational circuits, level 1, level 2, flip-flops. We'll see here flip-flops. Okay, flip-flops. Okay, so if you see this one, just D flip-flop. Okay, if you see the D flip-flop, so if you see the D flip-flop, yeah, see here. So just I'm expanding this. See here. So this is 1 second. Yeah, see here, module. My module name is D clock reset Q bar. Okay, input D comma clock comma reset, output reg Q and Q bar. So here like I am using what? This is passage of clock means what? Synchronous. This is nothing but synchronous reset. Okay, suppose if I want to write asynchronous reset, so R, so I need to write negate of clock. Negate of clock. Okay, then it becomes asynchronous reset. Okay, so begin, if reset equal to 0, I am initializing begin, Q equal to 0, Q bar equal to 1, and else D equal to else if D equal to 0, So begin q equal to 0, q equal to 1, and if it d equal to 0 means what, just it is following, just it is nothing but sequential buffer. Okay, and else begin else q equal to 1, q bar equal to 0. Okay, or otherwise you write you can write so in order to write this one, you can write else d equal to so q equal to d also you can write. Okay, so this is the Verilog code. Coming to the test bench, see here, this is the test bench. So here expand this, see here, so module d underscore d flip flop tb. So outputs you need to initialize with y data type, and input you need to initialize with reg data type, and I'm instantiating. Okay, so that is that is a design name. What is my design name? D flip flop. This is my instance name. Instance name is optional, you can give any dut, uut or insta, anything, any name you can use. And this is nothing but what, connection by position with order list. Okay, this is nothing but what, connection by position with order list. Okay, I told you, no, connection by name and connection by position with the order list. Okay, initial begin. So here you need to make clock equal to 1, and d equal to 1, and reset equal to what, 0. Okay, this is so you need to, I think you need to run for you are making reset equal to 0, no? So this is we need to make reset equal to 1 only. Okay, so why? Because when reset equal to 0, we are using asynchronous active low reset, no? So when reset equal to active low means what, reset becomes the output becomes 0 when reset equal to 0. Okay, so I need to run for 200 time units. Okay, and always hash 5 clock equal to not of clock, always d equal to not of d, and always reset equal to not of reset. Okay, 50 time units and module. Okay, so this is my test bench. Okay, so just this I am going to run in the what we call this Vivado. Okay, so I am opening this. Costa sim also you can write. Okay, so this is here run file is there. Okay, Costa sim also I will show you, or model sim or Costa sim, both are same only. Here one more run file is there. Okay, run file. So if you go to that folder and keep on that do space run dot do, so this is my run file. Okay, normally vlive work, vlog, vtb, and this one. Okay, vopt.org, this commands I need to run. Okay, so I'll show you in Custasim also, and Xilinx Vivad also, so that you will get some idea how to execute these programs. So I'm opening this Xilinx Vivado. First you need to create the one project, no? So new project. So I'm creating one project. Those are nothing but sequential circuits. Okay, sequential circuits. Okay, sequential circuit, this is my project name. Okay, sequential circuits. So you need to find out the path also, so where this project is saving, this path also you need to find out. That means you create one folder, that is RTL code using Xilinx Vivado, or like that you create one thing, and you make this this one. Next, and here create your source file. Okay, so what is my source file? D flip flop, no? So just this one only, module name you give. Okay, this copy this, and you paste in this. Okay, next, and finish. Okay, so project will be created. Yeah, it is asking like module name is okay. Yes. Okay, so yes, So that my source file is created. Okay, so here this is my source file. Okay, so design source. So just here just you remove this is not required. So time scale is 1 nanoseconds per 1 picoseconds, means this is precision, and this is my delay. Okay, this is 1 nanoseconds is my delay. Okay, so here if you see just copy this code, just copy this code and paste in the Vivado. Okay, save this. Yeah, save this. Okay, and in the simulation source, add the source, create, add. So create my test bench. Where is my test bench? Here TB is there, no? So D flip flop TB. This is my test bench file. Okay, so create the simulation source. Okay, so copy this and create your file. This is my simulation file. Finish. So my module name is also same file. Just create that. Okay, so here this is created, where this is created. Okay, so just remove this. This is not required, so delete this, and this one TB file is there, no? So this one just you copy this. Okay, and you paste in this and save this. See here. So now what happens? So this is created. Why? Because I instantiated this design in my test bench. Okay, so this is my design. Okay, normally in the test bench I instantiated. Okay, that's why it is created. Okay, suppose if you want to see the design, so open the elaborated design. Open the elaborated design. So this is reading the netlist and it is creating the design. Okay, it will take time. Syntax error. Okay, where I got syntax error? 1 second. I'm getting syntax error. Yeah, something I wrote the D flip flop file. Okay, 1 second, I will show you. TL codes D flip flop. This is D flip flop. RTL. Okay, this file I will use. Just this file I will use. D flip flop asynchronous. Yeah, this file I will use. Okay, somewhere copy this and save in this design file. Okay, save this. This is passage of clock and not of reset, and test bench also. Second test bench TB file or TBD asynchronous. This is asynchronous reset. Okay, so asynchronous reset. This one test bench. Copy this and yeah, save this file. Yeah, see here, that means this is same only. So like I'm using connection by position with order, connection by name. Okay, so here this program, this is also same D flip flop only. So here suppose if you see this one, First I will explain the code. This is asynchronous active low reset. Okay, asynchronous active low reset. Okay, module D flip flop asynchronous reset. So input so separately I need to include. Okay, so input wire clock, input reset underscore n. So this is the representation for what asynchronous active low reset. Input wire D, output reg q, always at the rate passage of clock or negate of reset begin. Okay, if not of reset, I am initialized in q to 1 tick binary 0, else q equal to d and end module. Okay, so this is my design. And test bench, if you see, so module tb d flip flop asynchronous reset underscore n, and whatever the input variables are there that I need to initialize with reg data type, output variables are there that I need to initialize with y data type, and need to instantiate. Okay, which is connection by name, you need to instantiate with vertically like this. You need to instantiate. Why? Because suppose if your design is having 100 inputs or 150 inputs, okay, so you need to instantiate like this only. Why? Because it is easy to trace your inputs and outputs. One input is missing, it's a suppose when you are using connection by position with order list, so there is difficult to trace that missed input or output. Okay, so better to use connection by name only, clock reset d and q. So whatever the inputs are there outside the bracket are nothing but design inputs, and whatever the inputs inside the bracket are nothing but test bench inputs. And initial clock I am making 0, always hash 5 clock equal to not of clock, generating the clock. And integer I, so integer I means I am using for loop. Okay, normally I am using for loop. Okay, so reset underscore n equal to 0, d equal to 0. Here what I am doing, I am asserting the reset. Okay, I am asserting the reset means what, I am applying the reset. After 10 time units I am deasserting the reset. Okay, reset underscore n equal to what, 1. So means how I am giving the test cases means by using for loop. Okay, for I equal to 0, I less than 8, I equal to I plus 1, d equal to I of 0. Okay, and I am running for 10 time units. Okay, again I am asserting the reset underscore n equal to 0, hash 5 reset underscore n equal to 1, I am deasserting, and again I am giving some test cases. Okay, so this I want to execute. Okay, so just you can generate the waveform also. So run the simulation, run behavioral simulation. Yeah, you see here. So I think I displayed, I'm not displayed, I'm not getting in TCL console. But if you see the waveform, see here. So fit to page. Normally, like, so here if you see clock, so clock, this is my clock. So reset underscore n, initially reset equal to 0. So that means this is nothing but reset mode. Okay, reset mode. So what happening during the reset mode, I am getting what, q equal to 0 only. So when it is going from reset mode to functional mode, okay, see here. So that means you are getting the output immediately or not get output. You will get the output during the passage of clock. Okay, during the passage of clock only you will get the output. Okay, and see here. So it is following like D is following. So D is what? D is 0 only. So Q is following D. Okay, Q is following D. And next if you see, so that means here q is not following d. So when it is following d, during the next passage only, during this edge only, that following this d. Okay, and during next passage d becomes 0, q also becomes 0. Okay, it will be 0 till the next passage. This is next passage. Okay, and similarly till next passage, so it will follow the d input and it will be 1. After next passage d is 0 and q also 0. Okay, and during next passage also, so d is 1, q becomes 1. Okay, and here you see, so that means here so d q is 0, d is 0, q becomes 0. Okay, during next passage d is 1, q is 1. Okay, it's a sequential buffer, it is following the input. And here if you during this passage, here you see, that means here in this position reset is applied, reset is asserted. Okay, so when the reset is asserted, that means reset removal is what, synchronous with the clock. Reset removal is synchronous with the clock, but reset applied is asynchronous with the clock. Okay, respective of whatever may be the input here input is 1, but irrespective of clock, it is going to 0. It is going to 0. Okay, so from this you can find that this is mainly asynchronous active low reset, and here you see, so that means now again reset is removed. Reset is removed means during this passage of clock only, output is following the input. Okay, so that means D is 1 means output is 1. Okay, similarly for the negage of clock, D is 0 and clock is 0. Negage of clock, D is 0, clock is 0. During this passage of clock, D is 0, D is 0, Q is 0. During this passage of clock, D is 1, Q is 1. During this passage of clock, D is 0, Q is 0. During this passage of clock, D is 1, Q is 1. During this passage of clock, D is 0, Q is 0. Okay, just during the edge only the output is changing. Okay, so like this you need to analyze these inputs. Okay, suppose if it is Questa sim, so if it is Questa sim, so what you need to do, I created a do file or not. Okay, yeah, a D flip flop run file. Yeah, I created this run file. Okay, so first what you need to do means, first you need to open the Questa sim. Okay, Questa sim or a model sim, anything. Okay, so I'm opening this Questa sim. So just first you need to go into this folder. Okay, so what is my folder? This is nothing but D flip flop, no? So sim file, here I created work function, no? Okay, yeah, work function I will delete. Okay, here I will delete. So here in the sim folder, so this copy this path, cd space flower bracket, you copy this path. Okay, copy that path, save, and pwd is nothing but present working directory. So where I am there, okay, I am there in this directory. So what I will need to do, so in this present working directory, this is asynchronous reset, this is run file, this is my run file. Okay, I wrote in gvim. Okay, so I wrote in gvim, this is my run file. Okay, so this is my run file. Where is that run file? One second, I will close this. Yeah, run dot do. Okay, yeah, so here this is my run file. Yeah, okay, so I'm copying this. Okay, just rename, I'm copying this file. So in this do space run that file. What is my file? D underscore asynchronous reset underscore n run dot do. Okay, so paste this, so we'll get the simulation. Got one error. Okay, one second, I will show with some other programs. Okay, suppose all gates are there, suppose all gates, this is my all gates program. So here I created in the sim folder run file. Okay, so first you need to create the work function. Okay, work function you created. Okay, one second, I will copy this file, sim folder, sim. Okay, first you need to quit sim, quit hyphen sim. So quit sim passed up. One second, I will open. I want to quit. Opening Questa sim. Work is empty, no? Okay, First you go to this folder, okay. uh, this run file is VLive work is also there, okay. You go to this folder, you copy this, okay. So here cd so paste this, okay. pwd present working directory, do space run dot do. Yeah, simulation will start, okay. Simulation will start, okay. So here wave also started, just wave just here you bring this side, yeah, wave is there, okay. So here yeah, so you need to go to, that means you can, so no, so no means so here wave is there, so wave just expand this and fit to page. This is fit to page, okay. So these all are nothing but waves are already added. So here what happens, this is nothing but input and output, okay. Input is 2 bits, okay. Input is 2 bits, and these are the outputs for AND gate, buffer, NAND, NOR, NOT, VAR, OR, XOR, XNOR, okay. For different values of 0 0 0 1 1 0 1 1, I can see the simulation, okay. So directly with one command you can execute that code, okay. You can execute that code, okay. I think here also it will be executed. Suppose like 1 second, I am going to this training and development, my SIG, this Verilog codes are not Verilog codes. So which codes, level 2 flip-flops, suppose D flip-flop is there, so D flip-flop, so I need to copy this path, so just quit minus sim, okay. I'm coming out of the sim, okay, coming out of the sim. So cd flower bracket, paste this path, okay. pwd present working directory, okay. I am in that directory, D flip-flop, do space run dot do. So I will see whether my program will execute or not. See, directly I will get the output. So for each and every code, if you are running in the Costa sim or model sim, so you need to write for do file also, okay. So see here, so this is my output, fit to page, okay. So for different q and d input, whatever I explained, that you are getting, okay. This is my q bar and d, okay, clock, okay. During the passage of clock only the output is following the input, okay. Output is following the input, okay. Like this you'll get the different inputs and outputs. Like this you can analyze for the D flip-flop, okay. So hope you understood today's session, okay. We discussed about the test bench, and we discussed about test bench for D flip-flop and SR flip-flop, and we seen how the waveforms are coming, okay.